Hey folks, for this screencast, we're going to go over how to use one of these pulse sensor amped sensors from Adafruit website on a Circuit Playground Express. And so what I had the student do is purchase this, wire it up to their Circuit Playground, and we got the red wire plugged into the power line, the black wire plugged into a ground uh, plate, with the alligator clips, and then this like blue purple color here was hooked up to an analog pin. If you buy this sensor at the bottom here, there's this Adafruit Learn page, and there's this whole code that goes through it, and this is in Arduino language, and so this is like saying, hey, this code works with an Arduino Uno or an Arduino Pro. And they do a bunch of interrupt timers, and there's a bunch of logic here and things like that. And I could have looked a little bit deeper to find code that worked in Circuit Playground, and I think my student did find that, but this is their final project, by the way. And what I noticed, though, in all of these codes, is that they're just reading the analog pin from there. And so the Circuit Playground Express has a 16-bit analog digital converter, and so I said, like, let's just wire this up. Let's just wire up this sensor, and then since you have a pretty significant pulse in your thumb, just hold the sensor with your thumb, and let's just measure that digital output and do some post-processing on it and see if we can get the digital output that way. And then rather than like debugging it on the Circuit Playground Express and trying to get somebody else's code to work, let's just do it offline and then move it over to the Circuit Playground. And so that's what this video is here. Is I had the student again hold the pulse sensor with their thumb for a couple, like probably 20 seconds, and get a bunch of digital output data. And so this first column here is that 16-bit digital output signal from the analog digital converter, and then the second axis or the second column is time. And so I have this example code here already that imports numpy and matplotlib. It reads in the data. Here's the data from this side. So I put the delimiter as a comma because the numbers are separated by a comma here. And then I have my digital output as the first column, time as the second column. And then I have this minus equal in here just because I like time to be shifted over to the left. And then I plot here. So if we run the plot, you'll be, I was greeted with this nice plot. And, as a human looking at this, I mean, it's clear that there's, pulse, 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 pulse. And so we can do like a quick back of the envelope calculation, and we can grab, say, 5 seconds of data, and it's clear, like there's a pulse, there's a pulse, there's a pulse, and if there's 1, 2, 3, 4, 5, 6, 7, 8 pulses over 5 seconds, and so 60 over 5 is 12, and then 12 times 8 is 80 plus 16, 96. So I'm looking at this, seeing a 96 beats per minute heart rate. And so that's a little high. I think the normal range for humans is like 60 to 80. But after I do a long workout, like even after a couple hours, like I'm really tired and my body's like replenishing itself. So 96 doesn't seem that out of the ordinary. And so we're going to go with the beats per minute of 96 BPM. Now, we could go through here and write a code that just like gets the BPM and just grabs all the data and then says like, hey, this is the BPM. But I don't really want to do that because, ooh, we're getting some glitch here. Okay, I don't want to do that because, come on, you can do it. What I'd like to do is pretend, right? Pretend that the data is being sent to us in real time, right? And real time. This way we can copy code to the CPX easily, right? And so I almost want to like animate the data, if you will, but first what I need to do is figure out how exactly I want to capture this data. And so the way I'm looking at this is that I'm seeing one pulse that's really big, and then a smaller pulse, and then a big pulse, and then a smaller pulse, and then a big pulse, and then a smaller pulse. Now, I am every now and then seeing like a third pulse right here, and so we either need to filter out that like third pulse there, or we need to have some criteria that basically says like, hey, if you take the first pulse and the second pulse, if that third pulse is like way smaller than the other two pulses, then just throw that out. And so basically what I want to do is I want to like count peaks in real time and then save the time that I see a pulse and then wait for a smaller pulse and then another big pulse and then take the delta between those two pulses and call that my pulse. So what I'm going to do to sort of simulate this in real time is I'm going to say, okay, for I in range of 0 to len of time in this case, I'm going to, I almost want to comment this out. I kind of want to plot, I want to see if I can animate this. I think that would be very neat. So let's do like a plt.figure, because when you're using Mu Editor, you can actually use the plotter. You can see the plot in real time, and so I kind of want to like replicate that. And so I think you can do like a plt CLA. I think that's a function. And then let me see if that actually is a function. Looks like that's fine. All right, so I'm gonna go ahead and stop it. And then, so we're gonna clear the figure, and then what I'm gonna do is I'm gonna plot time from 0 to I, comma, do from 0 to I, and then I'm going to set the xlim, I'm going to make that go from 0 to time minus 1, the end time, and then, it looks like I'm missing parentheses somewhere, there we go, and then the ylim, I'm going to do, I guess the np.min of d0, and then np.max of do. And then I guess I'll pause for like 0.01 seconds. Let's see if that works. It's been a while since I've done this before. Yeah, so that's super cool. So there's kind of our pulse going in real time. Okay, and we're gonna stop this. 0.01 seems like it's too slow. I also want a grid, and then I'm going to run that real quick. Okay, so hopefully there's my data running. So there's the small pulse, the big pulse, small pulse, the big pulse. Looks like there was like a little, yeah, there's like that little pulse right there. It's possible my computer's just lagging, and so maybe this isn't working very well. But this basically replicates, you know, what this would look like in real time. And so this is just like an animation script right here. So we can kind of see this happening right now. We're going to replicate the CPX here and say, okay, I know what my time is, so I'm going to say time monotonic, because that's a function on the Circuit Playground Express, is time of I. And then I'm going to say that my current digital output, DO, so I'm going to call it like analog value, is going to be DO of I. And so what we need to do is we need to detect when there is some sort of peak. And so one thing I was thinking would be a good idea is to get like a derivative signal and then plot when that derivative changes sign, but then like filter that signal so that I lose that like third one, or you know, first find the peaks and then removes the ones that are like smaller. I think for debugging purposes, I think this is going to be really hard to do in sort of real time like this. So what I'm going to do is I'm actually going to block comment. I don't know if you knew you could do that. I'm going to block comment this, and I'm going to do what I just said, assuming I have the entire data set, and then go from there. And so I'm going to do a PLT plot. Let's first take a derivative. So I'm going to say a DDT of DO is going to be DO of 1 to the end, right? I think you just do it like that, minus DO of 0 to the minus 1, because I think it ends right before it. And then I'm going to divide that by time time that goes from 1 to the end minus time from 0 to minus 1. Okay, and then I'm going to PLT figure, I'm going to PLT plot time, and unfortunately when you take a derivative you lose a data point, and so I have to go from 0 to minus 1, and then I can do DDT of DO, and then I can throw a grid on there. I'm going to go ahead and throw an X label on there, time in seconds, Y label, and that's going to be D0 dot, right? Which is sort of like DO per second, which is a weird unit, but it is what it is. Okay, so let's see if that derivative worked. And so I think what we're going to need to do is sort of line this up. And basically, wherever we see a 0 crossing, so let's see if we can zoom in from 0 to 0.7. Let's see, 0 to 0.7, so that's about there. And so wherever we see a 0 crossing is a peak, and it's from positive to negative of the peak. So there's a peak right there, peak, and then we're going to go, here's from negative to positive, so there's a peak down here, and then right at like 0.3 seconds, there's a positive slope to negative, which is this 0 crossing right here. And so everywhere there's a 0 crossing is a peak. And so, oops, I wanted to do the pan button because I saw something interesting. So, okay, no, that's fine. And so this might be like a third peak here, this 0 crossing, but again, if the derivative goes from positive to negative, and again, we might need to filter it, there is a peak. And so I think we are actually going to have to do this looping here, but I don't want to do this PLTA or this pause. Yeah, so let me get rid of the animation part of it. And we'll do the animation part later, and also the replicate CPX part. We'll do that later. But what I do need to do is, as I loop through time, I need to find where there's a 0 crossing. So basically, I'm going to find 0 crossings. And let's see, I'm also going to move these down so that I can plot everything all together. So here is take a derivative, right? And then down here, I'm going to plot, so this is plot raw data, and then here is plot derivative. Okay, so the first thing is find 0 crossings. So basically what we're going to do is we're going to take the DDT D0, we're going to say sine of DDT is there a sine function? NP dot sine of 1 or minus 1? Like minus 10? Yeah, or like positive 20? Okay, cool. So we're going to do sine of DDT is going to be NP dot sine of DDT of D0 of the first data point. And then if the sine of DDT is greater than 0, so let's go back, let's get rid of this and plot this again. We want a 0 crossing. To find the peak, we want a 0 crossing when it goes from positive to negative. So basically, if the sine is currently positive and NP dot sine of DDT of D0 of I, which we need to start, let's do plus 1, because I need to get the next one. If the next one, well, really what we want to do is like the last, it's either way. We either have to do the last one or the next one. So we're just going to do the next one and loop till there. So if the current one is positive and the next one is negative, we have found a peak. We found a zero crossing. And so what I'm going to do is I'm going to say zero crossings is this. And I'm going to say time at zero crossing is right there. And then I guess I'm going to say d0 of the zero crossings is right there. And so if the sign is positive and then it goes negative, I'm going to say the time of zero crossings dot append. How is that function called? Is it crossings with an S? Crossings dot append time of I, right? And then D0 zero crossings dot append D0 of I. Okay, so I'm appending that matrix. Then after I loop through everything, I'm going to convert to numpy arrays, otherwise you can't plot. I'm going to say time zero crossings np.array time zero crossings, and then d0 of zero crossings is np.array of d0 zero crossings. And then what I'm going to do is when I plot this raw data, I'm going to plt.plot time zero crossings, comma d0 zero crossings. And I'm going to do blue stars. And I'm going to run that. And I should hopefully see, doesn't like it. Index is out of bound. I thought I did -1. Oh, the derivative is -1. Because you lose a data point when you take a derivative. Aha! This looks terrible. We have problems. This is why we debug. Okay, let's see what's happening here. So, oh dear. Oh, we're picking up the peak, but we're picking it up because we forgot to save, like, hey, by the way, sine ddt is equal to np sine ddt of d0 I plus 1. Otherwise, you don't actually capture it. And so we need to make sure that we update that one. Okay, so we're debugging. That's what we're talking about. Now, I think we're lagging a little bit. Like, we're like lagging. You see that? And then like here, like all of these peaks, we're lagging. And so I think what we need to do is do a +1 here, and then a +1 here, and then, you know, run that, and we're good to go. Okay, so now we've captured a peak, captured a peak, captured a peak, captured a peak, 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 and so this is what I was talking about, is that there's a peak right here that we need to get rid of. And I don't want to just say like anything under 45,000 is not a peak, because if you scroll over here, like this is clearly a peak here. And actually, what happened here? We missed this. Oh, it's because it was flat. Interesting. I guess I'll put it equal to 0 there maybe, because it was positive. And if it equals 0, that's fine. So we had another debug issue. Did I get that flat one? I'm not sure. Let's maximize this and see if we actually captured everything. So we're capturing everything, and like I said, I don't want to just cut everything off at 4,500, because there's a data point right here where it's not 4,500. Ooh, and then we captured 2 peaks there. That's no good. And that's because I think it like saturated there, so there was like a little bit of a fluctuation. And so there's some filtering that we need to do to get this to work properly. Okay, so this one's an easy one to do. So what we can do is we can save the time that we captured it. So what we need to do is we need to have like first peak time is I guess 0, and then we're going to do d0 peak value is 0 for this time. And then what I want to do is, if we detect a peak, we're going to say, okay, first peak, I guess second peak time is time. Oh, let's do, if we detect the peak, second peak time is time of I plus 1. Okay, now, if second peak time minus first peak time, I'm going to say is less than something ridiculous. So if your heart rate is like 300 BPM, 300 beats per minute is, what's the delta between them? That's 60 over 300. So that's every 0.2 seconds. So if that peak is less than 0.2 seconds, I'm going to say greater than 0.2 seconds, then I'm going to say you have appropriately identified a peak. Okay, so let's check that real quick. Let's see if we fix that. There was one in here where it's like saturated. It still grabbed it. So what is this value here? This is 6.37. Yeah, that shouldn't have. Oh, did I forget to save first peak? I forgot to save first peak. Okay, so if it is greater than, then I need to save first peak time is now second peak time. There we go. And then hopefully that will reset the counter. And then if we come up here, bada bing, bada boom. Okay, sweet. So we've basically said like it's impossible for you to have a BPM of 300, and so we have appropriately filtered that out. All right. Ooh, problem is we lost a couple peaks. Oh, it is because of that third peak. Okay, so now there's a problem. So the filter is working for the peak happening too quickly. The problem is that this third peak needs to go away. And this is where I was saying we need to find, like this right here is not really the first peak. Oh, and it's fine because I set it to 0. That's not really fair. What I really need to do is set this first peak value to like, minus 1 each way, because you don't really know when it's going to start. And so that will give us, okay, so that gives us that first data point again. But the problem is every time we get a third peak, we don't pick up this value. So what we need to do is we need to figure out how to get rid of these third peaks here. And there's a couple. Okay, so how do we get rid of that third peak? Let's see. Okay, I'm going to pause the video and think about this, and I'll come back. Okay, folks, so I got a pretty cool situation here. So basically what I did is I actually started creating like a running average and a running standard deviation. And basically what you do is you find that 0 crossing, then you check to make sure that like the distance between two peaks is appropriate. Like if it's less than 0.2, then you have a 300 BPM, and that just doesn't make sense. So you throw that one out. And then you check for a false peak. So what you do is you say, okay, take all of the peaks that you've found in the past and average them together. If the peak that you found is lower than, and I had to tune this, I said 1.2 standard deviations. If it's less than that, then it's probably a false peak. And when I do that, when I run it, I've completely removed not only the third peaks, but I've actually removed the second peaks, which is actually kind of nice because it means that I've captured it. And again, because you're using that running average, even this little dip here is like within that standard deviation, so everything's okay, and you still get those peaks. So at this point, now that you know what the peaks are, once you've found a peak, all you need to do is compute the BPM, which is first you find what's going on here? Okay, first you find, I guess I'll say compute BPM, and so first you find the delta time, right, between peaks, and so that is your time of I plus 1 minus your, actually it's just your second peak time minus your first peak time. That's your delta time. And then in order to get the number of beats per minute, you just do 60 divided by delta time, and then you print BPM equals BPM. And then we should get infinity. That's fantastic. Where do I save second peak time is time of I plus 1? Right there, first peak time. You need to move this down here, otherwise it's just 0. Okay, there we go. So I guess here, this is like peak found, time to update values. Okay, and then we're gonna run this. There we go, cool. And so there's the BPM being recorded, and so first BPM is ridiculous, second BPM is 184, and then it finally settles out 105, 97, 95, and then that kind of bounces around from there, but it's pretty much like plus or minus whatever. And so that means we got it. That means it works. And so now let's get the animation script. First, let's go ahead and, oh my goodness, I'm sorry, I hope you didn't hear that. Let's do a save as and call this pulse realtime.py. And then let's get this animation script going. Let's replicate the CPX where I'm, let's see, reading the current time and digital output values. And then you can't, so sign of DDT is up here. This is where you initialize it. So I'm going to just initialize this to positive because I don't know what else to do. And then let's see, DDT of DO, you can't do that. You have to take a derivative. And so what you need to do is you need to take DDT of D0 is equal to the current analog value minus the previous analog value over the current time monotonic minus the previous time and then you say the previous analog value is equal to analog value, and then the prev time monotonic is equal to time monotonic. Okay, now you have to initialize these things. So your prev time monotonic, I'm going to just equal set to -1, and then your analog, your prev analog value, I'm going to set to 20,000 because it doesn't matter. The first data point is going to be garbage anyway. Okay. Second peak time is not going to be time of I plus 1. It's going to be time monotonic because that's what I have. Second peak time, first peak time, that works. Your digital output is not going to be DO, but it's going to be the analog value. DO peak value average, peak value standard deviation, that's still good. We're not good. Well, we can save. I think this still works. We can save the values monotonic. And then this isn't going to be digital output. This is going to be the analog value. And then peak value average, peak value standard deviation, I think that's still fine. This is going to be a situation where like those arrays are going to grow so large that eventually like they're going to be really big. I also don't know if you can do the mean function on the circuit playground, so we may end up having to like write our own, but there might be like a math function that we can use. And then BPM I think is fine. Second peak value, first peak time, I think that's all good. And then sine DDT is just going to be sine of DDT. So we're just going to get rid of the array component of it, and I'm going to pray that that works. I think what I would like to do though is that like if I find a peak, I'd like to plot, let's plot 0 crossings, comma, DO 0 crossings in blue stars. And then let's run that. see if we get an error. Yeah, we broke something. We got an error and I couldn't see what it was. Let's see. Sign DDT and sign. Oh, whoops. Yeah, okay. So that just needs to go away. Does this work? I hope. So we should detect a peak. Yeah, it's not working the way I want it to. And I'm plotting, I'm spitting out the BPM. So I broke something. So I'm printing the BPM, but it's not plotting my time. The blue stars. Why is it not doing that? Is it, oh, it's because the pause is right here? That's probably why. So actually here, let's just do this. Let's move this up here and just put it into the plotting routine and see if that doesn't freak out. Okay, so peak. Okay, so it's somehow my standard deviation limit is not working properly, and it's picking up these bottom peaks again. And so I think what that means is somehow my standard deviation changed. It's probably because like I'm grabbing the value at which it happens. No, it's still grabbing it. Okay, let's try 1.4. Can you do me a favor and print the BPM, print the D0 peak value average, D0 peak value standard deviation, because it was working before and now it's not. I don't know why. So there's the peak value average and standard deviation. Oh, and then I guess also print me the peak value, which is analog value. So when we hit one of those smaller peaks, so there's the average, there's a big peak, there's a small peak right there. Yeah, so this is what I'm saying. So, oh, I think I'm making this too big. That's what I'm doing. So I'm saying if the analog value is greater than that average minus 1 point, there's the standard deviation. That's what's happening. If I actually want to do like 0.8, my bad. I want to make it smaller. I'm making it more strict. So let's see. So peak, and then this should be too small, and then peak, and then too small. Yes. Peak, and then check out the BPM, dude. Let's go. 95. And then we should get another BPM. Boom. 92. And what I also want to see is let's also print out time equals and put the time monotonic, like that, and run that back. And then, because I'm also curious, like, basically how quickly is it updating my BPM? So 0.9 seconds it updates, gives me a new BPM at 1.5. So every half a second, it is spitting out my updated BPM. Yeah, around every half a second, it's giving me a new beats per minute. And so I think this code, right, I would say from here down, right, is how your I think you could just copy and paste this code directly into the circuit playground and it would work. The only thing that you would have to do is you'd have to set up your initializations, like you'd have to initialize these things. But you could just initialize those just like it is, and then drop this code in there, and you should get your BPM in real time. So I'm gonna call this a win, folks. And yeah, by the way, like it's actually kind of cool because if you notice, like the BPM is not constant, and that's because like this was literally like one of my students like holding this thing. Like her heart rate is not like a constant thing, like it's fluctuating, and so is the analog signal. And so yeah, this is really cool. I'm really glad I got this to work. And yeah, I guess I will upload this code and the data to my GitHub, and I'll throw a link in the bottom of the YouTube. And yeah, I hope you have a great day, and I hope you have an awesome week and an awesome year, 2024. Let's go.